Yeah, core propagation? Awesome. Okay. So in case you already know everything, 100%, let's help everybody out to do it. So in today's workshop, my goal is to take you from 0 to 1 on artificial intelligence. Mainly what we're going to be doing is that we're going to be building a neural network from scratch to take a bunch of handwritten digits and be able to classify them, right? This is kind of the hello world of machine learning algorithms. Now, I guess one of the questions you might be thinking, why exactly are we building this from scratch, right? Currently, building a neural network takes up 5 lines of code in total. So there's really no reason for us to do that, right? And I guess the reason that we're trying to do this is because, well, I guess I can tell you a little bit about me first. I've had the wonderful opportunity to work with some of the smartest people in the world, right? Whether it's at ISF or at various companies working as machine learning specialists. One of the things that I noticed is that the smartest people don't understand a lot of things, but they understand a few things at a very deep core fundamental level. So the objective here, what I hope to give you guys before we walk away here, is to make you even 10% better at understanding the fundamentals of what makes these amazing machines work, and quite frankly, what the future holds for us. Because this is probably one of the most transformative technologies we're going to experience in the next 50 years, and I don't take that lightly. So, shall we begin? All right, awesome. Let's do it. So, I guess the first thing to talk about is what really is AI, right? It's a little bit fuzzy, so let's just clarify that a little bit, right? So, the objective goal of AI, actually I'll use this software because it's easier for more of you to see, is basically to take some input, right? And then we have some box. Let's call that our AI for a second. And map that to some output. Now, our inputs and outputs here can be anything, right? So I'll give you an example. Let's say we have SAT scores versus trying to get into college, right? We have a bunch of data saying, okay, here's 1,000 students, and here are all their SAT scores, and here's whether they go into college or not. What we're trying to do is maybe train an AI to see, okay, if I have an SAT score of 1,500, what's my probability of getting into college? So the input would be the SAT score, and the output would be the probability of getting into university. And so AI here is kind of like a newborn child. It's really dumb at this point. Like if I give it like 1550, it might just output like a 0.1% chance of getting into university, right? It knows nothing about the world. So in that way, it's kind of like a newborn child, right? So has anybody actually like seen a newborn child here? Some people? No, kind of, right? Well, they're stupid. Quite frankly, they don't know anything about the world, right? So try to get a newborn child and try to explain it what a cat or a dog is. Try to get it to figure it out. It's not going to work, right? It doesn't, first of all, it doesn't know what language is. So you kind of, it's like failed from the first part. And second of all, how would you explain to somebody else what a cat is? Well, cat has 2 ears. What's an ear? Kind of get fuzzy there. Because some of, basically the things that humans do, we have internalized them based on intuition, but we can't articulate them. If I ask you, for instance, we're about to do pattern dish classification, right? What's a 6? How do you recognize a 6? To somebody who's never seen anything before, what's a 6? Yeah, you can say swirl, right? But what's a swirl? And AI doesn't know what a swirl is, doesn't understand language, right? So that's really the core challenge we face when we're developing models. These things are dumb. They don't understand anything, right? So the goal is, or at least the only way that we can so anyway, the only way that we can actually teach our AI models to do really complicated tasks like model SAT scores is to show it a bunch of examples. We don't need to explain these stuff because we don't explain to newborn children what a 6 or a 3 is either. We take a newborn child and we say, okay, here's a cat. Like maybe you're walking down a park, right? Here's a cat, here's a dog. And then maybe a couple of years later, okay, here's another cat, here's another dog. Over time, that child begins to collect a bunch of data of sorts. That's a lot of experiences. And then based on those experiences, you can say, okay, I think I kind of understand what a cat is based on what we've shown you. And that's actually how humans understand and reason things. And that's exactly what we're trying to do in our AI models here today. So everybody here familiar with functions? Yeah, okay. That's really what AI is then. A function. We're taking an input, we call it X. We have some f of X, which is our AI model, and then the output, which is what we actually desire. The thing about AI that's really neat, however, is that this function is tunable. As in, we don't know what this function is, but we can change that function to be more close to what we actually, well, want it to be. And that's really the core essence of AI. Now, the key question that you guys might be asking here is, well, what is this black box, right? It just says AI right now, and there's no intuition as to what it is. Well, the most popular type of AI algorithms today are that of neural networks. Now, how many people know what neural networks are here? Okay, one person. So basically a neural network, you can think of it as a bunch of tiny functions that are kind of smooshed together in a giant function. And I guess I'll just draw this out for you, right? So let's say we have some input. So we can go 1, 2, 3, 4, 5. And the neural network basically has multiple layers. So this is our input layer. We have a couple of hidden layers. In this case, I'll draw one to save space since we don't have much. And then we have our output. Let's get that. So I'll label this here. So input, hidden, and then an output. So the input layer is self-explanatory. We input a bunch of things. So I'll give you a quick example. Let's say we were trying to build an AI for detecting the probability that somebody is going to have a stroke, right? Maybe one of the inputs we would give them is the age, right? Obviously, higher age people are more likely to have a stroke. Maybe we would give them something like their physical activity, right? So maybe their physical activity. Maybe we would give them their BMI or something, right? So what I'm trying to say here is that we can give our AI multiple inputs. It doesn't just have to be one thing like it was with the SATs, for example. So now we have basically a huge list of inputs. And this list is actually called a vector. We good? Everybody's with me so far? Awesome, sounds good. So what this input vector might look like, let's say their age is 45, their physical activity, let's say 1, in the scale of like 1 to 10 if they were ranking, right? And then their BMI might be, I'm not sure how BMI is measured, but let's say 20 for whatever reason. But the TLDR is that we have a huge vector of input numbers. And this is the input to our model. What the hidden layers do is take this input vector and apply a bunch of transformations to it to eventually get it to the outputs that we actually wanted to have. So I'll quickly illustrate to you what's happening here. The job of the hidden layer is to weigh each of these inputs and see which one of the inputs are most important for the output that we're trying to figure out. So in this case, I guess our output's only going to be one node. And this node is either going to be 0.5 and above, or it's going to be less than 0.5. So this is going to output the probability that a person will have a stroke. Right? Above 0.5, you have a pretty high chance of having a stroke. Below 0.5, not really. So what the hidden layer is trying to do is say, okay, I need to weigh which one of these inputs will most affect the patient's ability to have a stroke. And that's where weights come into play. So this isn't just like a bunch of random circles, right? These are actually connected together. And each one of these lines is a weight. So let's say age, for instance, right? Let's say the age weight was 2. That means that it's kind of important. But let's say the physical activity weight, let's make that a 5. That means that physical activity was judged to be more important than age by this hidden layer, so to speak. The reality is, however, this is the fundamental problem of machine learning. We don't actually know what these weights are. And the job of the AI is to learn and fine-tune these weights so that it gives us the output that we actually need. And I'll get to that in a little bit. But I guess what we need to focus on right now is that each one of these inputs is being weighted by our hidden layer. Now, sometimes what happens, because remember, their weight is actually being multiplied by whatever this is. So if our age is 25, we'll have our weight multiplied by 25. What happens if this is 0? For age, it doesn't make sense, but sometimes we actually want there to be another term just in case our input is actually 0. So if you had, for instance, an SAT score, going back to our old example in college admissions, let's say you got an SAT score of 0. Well, if the weight was, let's say, 100, that would just go to 0, which isn't true because SAT score is still really important. We still want a weighting pair. So we can just add a random constant term. Maybe let's make it like 1,000, right? We can add some constant term, and this constant term is called a bias towards the weight, just in case that weight actually goes to 0. So I guess to sum this all up here, the way that this kind of works is that we have a huge matrix of weights. And everybody familiar with what a matrix is? Yes? No? Awesome. So we have a huge matrix of weights, right? So maybe if we take the first one, age, right? And we have 10 different inputs. So this will be like, I guess the length of this will be 10. And we have 1, 2, 3, 4, 5, 6 of those hidden layers. And so each one of these will just be a weight, maybe W1, W2, W3, W4, etc., for each of those 6 nodes, right? So W1 would be age with respect to this node, W2 would be age to this node, W3 for that, and so on and so on. So we have this huge matrix of weights, right? And then we obviously multiply that by our entire input vector. So that's what I talked about right over there. So this is basically our input. And then we have to add the bias term just in case some of these are 0 and we still want to weight them something. And so that is our bias. And this is actually the fundamental operation that kind of governs how machine learning works, right? We have a weight matrix, we have our inputs X, and then we have a bias. Now, does this look familiar to anybody? Wx plus b. Maybe that should ring a bell. Not particularly. It looks like y equals mx plus b, right? And that's actually what these models are actually based off of. And that's the problem with neural networks. You see, even if we have 400 different hidden layers, if all we do is wx plus b here, well, our model is really just going to be a line. It's just going to be a really long and fancy way of expressing a line. And the reality is that most problems in this world are linear, right? Even exponential growth, our model won't be able to actually, I guess, represent if we just have a bunch of wx plus b things. And that's where we need something called an activation function. We need something that can take this wx plus b representation and something that can actually convert it so that we can represent more complicated systems. And for this workshop, I'm not going to go too deep into what those are, just in the interest of time, but there's only two that we'll be using today. One of them is called the ReLU activation function. So that looks like this. So everything that's, if your input's below 0, then it just gets 0. There's no negative inputs. And if it's above 0, it just leaves it to whatever it is, right? So if you had -5, 4, and 4, you pass it through ReLU, you would get 0, 4, and 4. That's pretty much it. There's nothing much to it. Just allows all the positive values and restricts all the negative ones. So pretty simple. Now, moving on to the outputs here. You guys might have noticed that these outputs are probabilities. And one of the things you might have noticed about probabilities is that they can only be between 0 and 1. We can't have a probability of 500, but this neural network is stupid and doesn't understand that. It might output -45 for all we care. So how exactly do we restrict that output between 0 and 1? That's where our second activation function comes in, which is called the softmax. And once again, not going to explain it in too much depth, but basically it looks something like this, where it's upper bounded by 0 and 1. So no matter what you input to this, it will only give you something in between these two, and it will basically ensure that all of your probabilities will sum to 1. Now here we only have one output node, so it's not too much of a problem, but in the hand vision thing that we're going to build today, that has 10, because we're trying to recognize between 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever, right? That means that we're going to have 10 output nodes, each one representing the probability that the number we inputted is going to be 1 or 2 or 3, whatever. So in those cases, we want all those probabilities to sum to 1, because they're probabilities. If they sum to 150%, then what are we doing, right? And that's exactly where that softmax function comes into play. Now we can just label these just in case, for number 1 and number 2. Cool. So that's pretty much how our network works. And I might even just draw a quick diagram for you so that we can, I guess, kind of visualize how this works, right, on a very high level. So first we start off with that input, okay? And we pass that input into the first hidden layer. That first hidden layer is going to take our weights for that given hidden layer with the input, which is the vector x, and add it to some bias, right? For everybody with me so far? This makes sense? Cool. Now, once this is done, remember that we want to add our activation function so that we can represent more complicated functions. So we're going to add that ReLU activation function right there, which I'll just call A1 for now. Now we have our second and final layer, which is the output. So we're just going to do the exact same thing again, right? We're going to do W2 this time. Remember the second weight matrix, multiplied by not the inputs, but actually the output of this layer, which was A1. And we're going to add that second bias term. Finally, all of this goes into the softmax function to restrict them into probabilities. So that becomes A2, and that's our output. Pretty simple, right? Not much to it, not a huge, complicated, hunking chunk of metal. Just very simple set of equations that we need to apply. And this is where things actually get a teeny bit more complicated. So you see, this entire process right now is called forward propagation. We take an input and we propagate it through all the layers of the network until we get to our output. Pretty self-explanatory. How do we fine-tune our network though? Because right now, as I said, these weights and these biases are just random. They're not initialized to anything useful. And we want to find the ideal set of weights and biases that lead to the best task performance. And that's how these neural networks actually work. Yeah?
You should put give the input and the output for the AI to like calculate and
sorry, maybe just speak up a bit.
And you should give the input and the output for the AI to calculate all the weights, biases, and
yeah, exactly, pretty much. And that's actually what we'll be talking about in a little bit. So in case, also correct me if I'm wrong, what he basically just mentioned is that we want to give our model a bunch of input data, a bunch of output data, and get it to figure out and tune itself based on how correct it is. And that's actually what we're going to talk about right now. So we need to figure out how good is the output that our model is generating. And we can do that by something called a loss function. So let's move on for handwritten digit classification, for instance. Let's say our model says a given number is a 5, but that number is actually a 6. Well, we want some way of figuring out how good is the model's prediction. And that's called a loss function, which I'll represent with an L. Now, these things aren't actually represented like 5 and 6, and I'll touch on them a little bit. But this loss function basically says, okay, how good is the output in comparison to what the data actually says the right answer is? So the loss function in this case is almost like a teacher of sorts, right? It gives the students a bunch of questions, it sees what it puts out, and it marks them as right or wrong, and gives the students an indication of how far it is from that correct answer. So if this was a 6, for instance, versus if it was a 10, that loss function would output different things. And obviously, the more wrong you are, the more crazy this loss function is going to get, which is what we want. And that is basically on a high level how the machine learning process works. And now we need to figure out just one last thing. How do we find those right combinations of weights and biases so that we can minimize this loss function? Now, in practice, let's say, to simplify things, that we don't have weights, we don't have biases. We just have one variable that we're trying to minimize, and that is theta, right? We just have one variable, theta, and we're just trying to find the minimum of that variable. So let's say that we started theta off at 0, right? And we just had a bunch of values. We randomly tested a bunch of values of theta. And this right here is our loss function, right? Let's say when theta was like -2, our loss was pretty high. Maybe if theta was -1, our loss was kind of low. At 0, it was really high. At 1, it's like kind of here. And at 2, it's like fine. What? So if we were to graph this, it would look something like this. Now, right now, what do you think is the best value we can set theta to? Oh, sorry. What do you think is the best value we can set theta to right now?
-1.
Exactly. Now, in case you guys didn't follow, remember that what we're trying to do is minimize the loss. This is basically how bad the network is. So the lower this number, the better our network. This is like, I guess it's like if the teacher told you how many answers you got wrong, right? This one, you got a lot of things wrong, almost nothing wrong, a lot of things wrong again, kind of nothing wrong, and a lot of things wrong again. We obviously want the setting where we get the least amount of things wrong because that's the best model. And so theta here would be set to -1. Now, here's the thing though. In practice, we don't actually have access to this function. Right now, you guys were kind of able to look and see, okay, this is the lowest value of this function. Therefore, that is exactly where we're going to set theta to. In reality, we only have a piece of this function. We might only have access to this. Then how do we figure this out? Right? It's a bit of a dilemma. So what some absolute geniuses did is that they invented something called stochastic gradient descent. And this seems it's going to be a mouthful, but it's not as complicated as you might think. Everybody here familiar with derivatives? Kind of? Yes? Just raise your hand if you're familiar with derivatives, basically. Okay, I'll just quickly re-explain it, right? So everybody know what a tangent line is? Right? Okay. All the derivative is the slope of a tangent line at a point. So at this point, the derivative would be a 0. So it's like how flat the point is. Just think about that. So this point is really flat, so the derivative is 0. This point is steep, and it's also negative. The slope is negative, so this might be like -5. This point is 0 again. This point is positive, so it might be +5, and et cetera, et cetera. So what we can actually do is, let's say we're theta such -2. We can find the derivative at that point, and based on how steep the derivative is, we can take a step in that direction and then just repeat the process. So I'll quickly re-explain that just in case it didn't make much sense. So if we have a function like this, right? Let's say our derivative is like -5. Well, this is a really steep derivative. So we can take a step in the direction of that derivative, and I'll explain how we do that in a second. But we can take a step based on like how steep that derivative is. Then once we're here, we can calculate the derivative again. Okay, now it's slightly less steep. So let's take a smaller step. Okay, now it's almost flat. So we can take a smaller step. And now it's flat. We've reached the minimum of the function, which is the optimal value of our parameter. Okay.
Would you use the derivative, like in this case, like use the derivative and then like use like find increasing and decreasing the intervals, because then you can like take the minimum?
So that's actually a wonderful question. And that would be amazing if we actually knew what the function was. But remember that the neural network isn't just one function. It's actually a bunch of functions that are stacked on top of each other, right? You have this huge function here, but each one of these layers is actually a function in and of itself. So the function doesn't actually look like that because we have millions of parameters, right? So almost imagine if you had a million different axes and you're trying to plot a function, you just can't visualize it, right? So if we can't visualize it, how do we find the intervals of positive and negatives? So that's why that kind of logic doesn't really work as we go to higher dimensions. Yep.
Using this method, it would probably stop at the first one. So how would you, what if there was a steeper one?
So basically you're saying like, if we started here, we would end up here.
Yeah.
Instead of there.
Yeah.
This one is amazing. That's actually one of the main problems in machine learning. Depending on where you start, you can get two completely different solutions. If I start here, I would get a kind of optimal solution, but there's a better one that exists. Now, in this example, it's pretty clear that this one is better than this one. Sorry, this one is better than this one. But in the real world, actually, it turns out that these local minima actually occur very close to these global minima. So it's actually not even a problem. And sometimes it's better to find these than these. Now, I won't get into exactly why that is here, but that is just what we've observed like empirically. So it's not really that much of a problem. So anyway, that's how this optimization process works. But now we have a million variables, not just theta one. So how exactly do we generalize this, right? And that is where we go back to back propagation. Sorry, I've been making really bad puns today. Back to back propagation. No laughs, no, all good. But anyway, so we have our loss function here, right? And this loss function, basically we want to figure out which one of these parameters most contributed to this loss. And before we do that, I'll just quickly label this so it's a better idea. So this entire thing is our second layer, and this entire thing is our first. Right, pretty clear. We want to figure out which one of these layers and which one of these parts inside the layers was the most responsible in creating the error, right? It's almost like if you were robbing a bank, right? You were like a police officer, you caught 3 people. One of them was driving the car, the other one actually robbed the bank, and the other one masterminded the whole thing. Sure, you can arrest the people who drove the car, the person who actually took the money, but what's really important is who masterminded the operation. That's who you want to arrest, right? It's a very similar thing here. Which one of these little guys actually contributed to that loss function? And that's what we want to figure out. And the tools that's which we figure that out is backpropagation. So as I said here, this is what happens when we have one variable. We can just take the derivative. But as I mentioned, we have multiple variables, multiple functions. So we have to do something called taking the partial derivative. As in, for every, basically what we do, we take the loss and we figure out how much did this contribute to the loss? And we take the partial derivative of the loss in respect to this. Have I lost everybody, or are we still, everybody understand what I'm talking about here? Partial derivatives? Yes? No, not really? Okay. Basically, you know how here I drew a tangent line, right? To this particular function? It's basically doing the exact same thing, except we're going to do it piece by piece for each one of those layers instead of doing it all at once for just one parameter. That's kind of how I would explain that, right? And also we can talk about this a little bit later if you guys like as well. Now, this is the last part of our machine learning calculations kind of thing. And the reality is that the actual derivation for backpropagation is a really long process. Like probably 3 hours of just sitting in a room trying to figure out exactly what the formulas are. Now, I happen to have those formulas right here. And this is going to look like utter gibberish, but I promise you, it will make sense if you actually sit down and think about it. For now, I'm going to give you guys the formulas so that when we build our neural network, we can actually just plug and chug and see what happens. So this hunky symbol right here is partial derivative. That's all it means, right? So this is for our second layer, right? Layer 2. Also keep in mind, when we're doing derivatives like this, it's like an onion, right? This is the outer layer of the onion, and we have to work our way inwards. So we have to figure out the derivatives of this. That's what's called backpropagation, right? We're going backwards. So we figure out the derivative of this, then this, then this, then this, then this, then this. All until we arrive all the way back to these. And that's basically how this works. So the derivative of the loss function with respect to the second layer. Now this is simply going to be our second layer outputs minus y. And this is basically this derivative of this first part, right over here. Now we do the derivative of the second part. This is, once again, the symbols look fancy, but it's really simple. We're taking the derivative with respect to the loss from this. Then we'll do the loss with respect to the weights, and then the biases, and then the same thing for the other, right? So this with respect to the bias term, or actually let's do the weights first. That's a little bit simpler. Weights term, so this M over here, this is just how many samples we have in our training set. So we might have, as I said, we have like 1,000, right? Then this would just be 1 over 1,000. It's pretty self-explanatory, I think. And we'll just take this again, so A2 minus Y, and we'll multiply it by A1 over there. Transpose, that's just a matrix term, we don't really need to worry about that right now. And then I'll squeeze in 1 right over here. I don't think I used the space that well, but it's all good. This is just going to be 1 over M. and then we're going to sum over basically this term where A2 minus 5. As I said, this looks pretty complicated, but if you actually sit down to derive these, they make perfect sense. So what I would encourage you guys, once you guys get home tonight, if you're interested in this stuff, actually see if you can figure it out for yourself based on basic derivative rules, if you can come up with these yourself. So all of this is for the second layer right over here. Now, let's do the first layer, and I'm running out of words. So all right. So I'm going to do this way over here. So I'm going to do the second part right over here. Here's the derivative of all the layer, first layer. For A1, we're going to do derivative of the loss with respect to A1. This is the most complicated formula you're ever going to see in this workshop. It's literally just, we take that second matrix of weights and we multiply it. This T is basically, think of it like multiplication for matrices instead of like numbers themselves, right? W2, and we're going to take A2 minus Y. And then remember that we added activation functions? Well, now we have to find the derivatives of those activation functions. And so that's what this G prime of A1 is going to be. That's then, of course, W1. And let's figure that out real quick. Partial derivative of W1. And this is going to look very similar to these two. So these two we can almost copy paste. The only thing that changed was the first like this part, right? It's the only thing that's different. Everything else is pretty much exactly the same because we had that activation Rayleigh function over there. So this one is simply going to look like 1 over m. And then this entire thing, which is the derivative of the loss with respect to the activation layer. So we're just going to write that exactly here. Boop. And oh, that's an 8, 1. And we're just going to multiply that by the transpose of the inputs. So this looks exactly like that. Except this time we just have the derivative of with respect to A1, and then we just have the inputs this time because we're back propagating, right? So remember the inputs for this was A2, which is why we have A2 down there, but the input for this was X. So now we just have to change exactly what we're taking the derivative with respect to. And last but not least, because I know we're probably getting tired of seeing a bunch of random things on the board, I was going to say screen. Derivative of the loss with respect to bias, and this is simply exactly what we saw there, which is the sum of all the derivatives from 1 to 1. Okay, now that's a lot of formulas. Once again, you guys don't need to worry about where they came from for now. I would encourage you to go back home and like search them up for now. But congratulations, because we've made it. And now we can actually take all of this knowledge that we've understood and learned and use that to build our very own neural network from scratch in Python. So everybody get out your laptops and let's make this happen.
We changed up even harder things line now. So you understand I saw once I explained what kilos, and then the other one make it just take out.
Interesting. Whoa. All right, let's figure this out. Hey, Nicholas. Nicholas, question: is the projector on? The projector doesn't seem to work. Projector isn't working. It's coming up here, but it's not. You know what? Right. Oh no! Oh no! This is not going to work. Oh no! Bro, why isn't this working? Oh, display. Okay, cool. So, what I'm going to need everybody to do on their computer, just type this URL right here, tinyurl.com/DL Scratch Workbook. So what I've done for you guys, because we're kind of short on time, but whatever, I've made a quick notebook for everybody, and I've loaded in the data set we'll be using and added some helpful functions for you guys. And we're going to be building the core logic of this neural network from scratch. So let me know when you guys are on that URL right there. The Wi-Fi? Oh, okay. Yeah. Also, in case you're wondering what the Wi-Fi is, well, guys, it's the Wi-Fi username, and so let's just do the password. Okay, so this is the Wi-Fi right here in case you guys are wondering. Sorry. Cool. All right, so everybody good? Sorry? Oh, that's Jocko Willink. He was a Navy SEAL, commander of Task Unit Bruiser in the Iraq War. Somebody I look up to, but ignore that. That doesn't really matter. Okay, cool. So is everybody on that workbook? You should see something like this once you're on there. Sorry? Deals. It should just be that. Is it working for everybody? No, it's not working. It's working. Guys, it does seem to be working. That's weird. Oh, it's L. That's L, not I. That's an L, guys. DL, like deep learning, DL, Scratch Workbook. Okay, that's not an I. Yeah. Yeah. Yeah, absolutely. All right, so basically what you guys should see is this notebook right over here, which is basically a notebook I've prepared for you guys in terms of the MNIST data set. So how many people are in right now? Half, okay, I'll wait like 30 seconds, then we can get started with the actual fun stuff. All right, we good? Awesome, let's get started. Okay, I'm gonna not use the mic because I think it's a little bit better. So basically what we're gonna be doing today is we're going to be taking a bunch of these images and we're going to try to build a neural network that can classify these, right? So this is something called the MNIST data set. Some of you guys might have heard of it. But TLDR, each one of these images are 28 pixels by 28 pixels. And each one of these images actually represents a handwritten digit, which we're going to try to classify. Now, there's a problem with this approach. Does anybody see the problem here? No? How do we input these into the neural network? What do we think? This is the picture, right? So far, what I've shown you guys is vectors of numbers. How we can work that? How does that work? Yeah.
Pixel number.
Exactly. So every image obviously is just a bunch of pixels, right? In terms of a black and white image, all the black spots are just 0, and all the really white spots are going to be 255. So we can unfurl this entire image into a huge list of numbers based on the pixel values of that particular image. And then we can feed that in as normal into a neural network and get our predictions. So let's start and get this done. So everybody's on this notebook, right? Awesome. So the first thing I need you guys to do is click here, File, and save your own copy in Drive. Just because if you guys do edit the master one, it will kind of mess everything up for everybody else. So everybody just make your own copy in Drive, and once you're done, just let me know. It'll be fun. All right, we all good? We all have our own copies in Drive? Cool, sounds good. So this part right here is just loading in the data set. So, and the MS data set is actually open sourced by Microsoft as well, so you can download it, but all you need to do, just take this cell here and click this button over here, which means running that particular cell. Now, this thing is called Google Colab, so you can run little snippets of Python code, one at a time, basically. And yeah, that's pretty much it. So click this, and this will basically download the data set onto, not your computer, but onto the server which this notebook is running on. All right, and this might take a little bit, but I'll just start explaining the rest of it in the meantime. So this right here will just print the first couple of rows, and when this executes, you'll see exactly what I said. You'll see a single entry that is 784 units long. Why 784? Because our image was 28 by 28 pixels, which is 784 digits in total. So it'll be basically a bunch of rows of 784 individual images, all stacked into one thing, which also kind of looks like a matrix. And that's what we'll be using today. So, first of all, has the first cell run for everybody? We're all doing that? Yeah, okay, cool, sounds good. Awesome. Now, this part right here, I mentioned that we're going to be building this neural network from scratch. We will need one slight tool, something known as NumPy, which will help us make those matrices and vectors, because PyTorch doesn't support them by default. But besides that, we can pretty much just use math and build this entire thing from scratch. So all you need to do, just run these first couple of cells until you get to building a simple neural network from scratch. Now, if you guys want to know what some of these upper cells do, I've commented the entire thing just for easy understanding. Awesome. So we good? Yes, no?
Yes.
You there? Awesome, sounds good. Now, the data set loading might take a teeny bit of time just because it's actually being downloaded from a cloud server at Microsoft. So it does take a teeny bit of time with these things, but in the meantime, I'll start moving on. And while this is running, you guys can start coding along with me as to the actual network. Now, the first thing we're going to need to do is actually initialize our neural network, right? We need to initialize the input layer, the hidden layer, and then the output layer as a whole. So what we're going to do, we're going to use NumPy for this as usual, because NumPy is amazing, in case you guys haven't used that. So let's do this. Let's set our first layer here. So this is going to be layer number 1. Yep, right here. So we're going to set the weights for our first layer. So layer 1 weights, and we're going to do np.random.rand. So this will just initialize that first matrix to a bunch of random numbers.
Share the link to the thing.
Oh yeah, so that is this right here, tinyurl.com/dl scratch workbook. Awesome. So anyway, we're going to initialize our first layer of weights right over here. And this is going to be the size of that layer. Now, in case you're wondering what these numbers mean, why it's 10 by 784, basically, remember that's our input matrix list. We have 784 samples, right? 784 pixels. And we have 10 particular classes that we can have in total, right? We can have 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. So basically what we're going to do is that our matrix will be of dimension 10 by 784. Now, once again, feel free to go through this again if you are a little bit unsure of things, but TLDR, that's what we're trying to do here. Now, of course, we need the biases of the first layer. So layer 1 biases, and we can set that also to np.random.rand. And this is just going to be 10 by 1. Now, in case you're wondering what this means, remember for a second that each one of the 784 inputs in our input layer has 10 connections, right? So if you visualize that as a matrix, it'll be connection 1, connection 2, connection 3, all the way through 10. And then for the next one, next sample, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and just repeat for all 784 nodes in our input. And the biases, as you'll know, we only have one bias per input, so we can just have 10 for those. Awesome. And layer 2 is actually pretty much the same as layer 1, right? There will only be one quick difference here. So let's just do layer 2. Now, you guys are probably wondering, why does layer 2 have 10 by 10, right? Well, that has to do with our hidden layer, which isn't here, but I'll quickly see if I can draw something, if you guys can see it. So if we have 10 nodes, right? Each one of those 10 nodes is going to have 10 connections, right? So let's say this is node 1, 1 connection, 2, 3, 4, 5, all the way down to 10. This is also going to have 10, and then so on. So you're going to have 100 in total. So you could arrange this into a matrix of 10 all the way to, well, 10 by 10 matrix, right? So this connection can be modeled by this connection, and then so on. Then for the second node, all the connections, then third node, fourth node, et cetera, et cetera. That's why that's 10 by 10. And once again, feel free to ask me about all of this, like once it's over, because it's really cool stuff. Now, that last layer right here, you see layer 2 biases. That is basically because we only need, remember, one. Oh, sorry. How much until you're done? Probably 10 minutes.
The other workshop is done. So.
Awesome. I'll wrap it up quickly then, probably. Awesome. I guess we're getting very deep into deep learning today. Can't keep track of the time. But anyway. That last layer right here, that's basically just whenever we have one bias for those 10 outputs. Yeah. Now, of course, we only have 5 minutes left. So in the interest of time, there is also a solution notebook that you guys can look at. So that is just going to be this right here. Instead of Scratch workbook, literally just type in DL Scratch solution. And that is going to give you the actual full, I guess, solution notebook of everything that we've built from scratch. So, oh, this is just loading right here. Now, I've actually gone ahead and did this, and this entire notebook is commented, so you guys can see everything that we've done and why it works. But TLDR, this is our forward propagation method. We take our inputs, right, and we just do the W times our inputs plus the biases, add the ReLU function over here. Then with layer 2, we take the layer 2 weights, multiply them by the activations from the first layer, and then add the biases. So TLDR, I know that we're kind of getting a little bit sick and tired of the math. So let's stop worrying about the math for a second and actually start seeing what this does when it's trained. So this is our model right now. This is a completed one because in this time we're able to build the entire thing. But what you're able to see is that our accuracy is actually improving over time, right? We started off at 35%. It is currently sitting at what? 86%. Okay, do you guys think we'll break 90? Yes or no?
Yeah.
Yes, okay. So this is basically working through all the principles I mentioned earlier in this workshop. On every step, the neural network is doing forward propagation. It's computing the loss. Then it's doing backward propagation to find out which one of its weights and biases it needs to tune the most to best improve class performance. Seems like we've broken 90. All right. We still have a little bit more to go. 91, 91.3, 5, 6. All right. Now 91% on MNIST is actually pretty, it's okay. It's not that good. Most networks state of the art achieve like 99% on MNIST because it's a very easy problem, right? So yeah, let's see. Okay, seems to have ended. 91.8 accuracy. And this is, by the way, without using any libraries, just building it purely from scratch. Now, this might seem a teeny bit confusing, but all we did here is we basically did forward propagation. Where's that? So we did forward propagation here. We wrote our ReLU and activation functions that I mentioned earlier, and we just did back propagation. And all of these things are just code implementation, so you can go and look at these, derive them yourselves if you'd like. There's also a really good article that I would 100% recommend for you guys if you're looking to do this. If I can find it. Nope, not that one. Anyway, perspective of that. TLDR is that just with code, just with math and matrices, we can create a model that can figure out how to recognize handwritten digits. And for cherry on the top, here's an actual example of our newly trained model predicting on some of the handwritten data sets. So right here, we can see our model. This is a number 6. This is what we fed into the network. Our model's prediction was a 6, and the actual number is also a 6, so that's good. Here we had a 9. The actual label is a 9, and our model predicted 9 as well. And we have a 1 here. This is kind of hard to see even for a human, right? Like what exactly is this? But the model was able to correctly classify this as a 1. So yeah, I hope this illustrated the power of deep learning to you guys. And once again, if you guys want to know anything, right here, you can feel free to ask me questions. And yeah, I hope you guys go home, try to build the rest of it from scratch yourself, see if you can do that. And yeah, let's get this done. Thank you guys.
Okay, let's go to the lecture hall.